नमस्कार दोस्तों, मैं शिवानंद उपाध्याय आपका स्वागत करता हूं हमारे YouTube चैनल केमिस्ट्री एकेडमी फॉर IIT JEE एंड नीट। दिस इज द 9th डे ऑफ JEE मेंस रिवीजन एंड वी आर गोइंग टू डिस्कस केमिकल काइनेटिक्स पार्ट 2। जो लोग हमारे चैनल पे नए हैं, जिन्होंने हमारा चैनल सब्सक्राइब नहीं किया है, उनसे अनुरोध है कि हमारे चैनल को सब्सक्राइब करें। वीडियो देखने के बाद आपको ये पसंद आता है तो प्लीज इसको लाइक करें। So let us start chemical kinetics part 2. In this chemical kinetics part 2, we are going to discuss about effect of temperature and catalyst on the rate of a chemical reaction. तो पहले हम Arrhenius equation के बारे में डिस्कस करने जा रहे हैं. So about Arrhenius equation, it is not valid for all chemical reaction. हमें ऐसा लगता है कि chemical kinetics हम सारी reactions की स्टडी कर सकते हैं, ऐसा नहीं है। हम सारी रिएक्शंस की स्टडी काइनेटिक्स स्टडी नहीं कर सकते। हमने रिएक्शंस को 3 पार्ट में डिवाइड किया है: स्लो रिएक्शन, फास्ट रिएक्शन एंड मॉडरेट रिएक्शंस। तो हम केवल मॉडरेट रिएक्शंस की स्टडी कर सकते हैं। तो केमिकल काइनेटिक्स में जो मॉडरेट रिएक्शंस हैं उसमें भी बहुत सारी रिएक्शंस है, सिंपल रिएक्शंस एंड कॉम्प्लेक्स रिएक्शंस, right? So we are discussing very simple reactions only, right? So, but the reaction which follow Arrhenius equation, for them we can apply this Arrhenius equation. सारी chemical reaction जो हम study भी कर सकते हैं, उनमें भी सारी chemical reactions Arrhenius equation को follow नहीं करती। तो जो reactions Arrhenius equation को follow करती हैं, उनके लिए Arrhenius equation valid है। So nobody is going to ask you that which reaction is not following or which reaction is following. If they are asking for us, if I have to see the effect of temperature, I have to use Arrhenius equation, right? So this is Arrhenius equation. K is equal to A e to the power minus EA upon RT, where K is rate constant for the reaction. A is, क्योंकि ये exponential term से पहले, so A is known as pre-exponential factor. R is universal gas constant and T is temperature in Kelvin. So something we must know about this Arrhenius equation. When we are writing this Arrhenius equation, K is equal to A e to the power minus EA upon RT. This formula is experimentally derived. Something which is experimentally derived is known as empirical formula. For those equations which are experimentally derived, there is no need of theoretical proof. Like force is equal to mass into acceleration. Newton's law is experimentally derived. There is no need of proof of Newton's law, because you are saying that by doing experiment, force is directly proportional to mass and force is directly proportional to acceleration, right? And then you are writing force is equal to mass into acceleration. So nobody is going to ask that by which theory we are proving that. Same way, all empirical formula is experimentally derived. Nobody can question, because there is an experimental proof that this equation is valid. So when we are writing this, K is equal to A e to the power minus EA upon RT, it is an empirical formula. On taking ln on both of sides, we can write that ln K is equal to ln A minus EA upon RT. And by experiment, when we are drawing the graph, we are getting some point at different values of temperature, 1 upon T versus ln K graph. And if we are joining these points, we are getting a straight line. So this graph is an experimental graph. So the intercept of this straight line and the slope of the straight line is constant. Intercept means here ln A, means the value of ln A is intercept. So A is constant. A is independent of temperature. For a chemical reaction, if it is following Arrhenius equation, the value of A is not going to change with concentration of the chemical species or temperature, right? So A is a constant. Similarly, the slope of this line is constant and the value of slope is minus EA upon R. So the activation energy is related to slope of this line. So activation energy is not going to change with temperature. So when we are discussing that Arrhenius equation is valid, A and EA are known as Arrhenius parameter. They are independent of temperature, concentration, pressure, right? For a chemical reaction, following Arrhenius equation, A and EA is not going to change. Now, in this Arrhenius equation, like if we draw temperature versus rate constant graph, rate constant is on y-axis, temperature is on x-axis. We know that K is equal to A e to the power minus EA upon RT. So when we are increasing the value of temperature, the value of rate constant is increasing, right? So how we are drawing this graph? In order to draw this graph, we are finding the slope at different points on this graph. So we are differentiating with respect to temperature because K is dependent on temperature. So dk upon dt is equal to K EA upon RT square. K is positive, always positive. Activation energy for us is positive when we are saying Arrhenius equation is valid. R into T square, R is universal gas constant, temperature in Kelvin is positive. So this whole right hand side is positive, means slope is positive. On increasing temperature, rate constant is going to increase. If I double differentiate this equation, I can write that d square K upon dt square. So I am writing differentiation of first function, right? So K is the first function. If I differentiate, I have differentiated K, then I was getting K into E upon RT square, right? So this if I say that this is first function, right, and differentiation of first function again will give you EA upon RT square. So K EA upon RT ka whole square, right? I am using the value dk upon dt is equal to K E upon RT square, and already this E upon RT square is there. So differentiation of first function is K, differentiation of this is equal to this into E upon RT square, and there is already E upon RT square. So we are getting this as differentiation of first function. Then second function का differentiation करेंगे. First function as it is है. We are differentiating this part. So we are getting minus 2 times of E upon RT cube. So this is related to differentiation of the second part. This is the first function and this is the second function, right? So now if I further simplify, I can take K E upon RT cube common, and from the first equation we are getting first term we are getting E upon RT, and from the second we are getting minus 2. So this is variation of slope, rate of change of slope with temperature. This is rate of change of slope with temperature. So we are getting that at what point the rate of change of slope is equal to 0. So if I put this is equal to 0, we are getting a temperature where rate of change of slope is equal to 0. So in this graph, this is the temperature. This value we have calculated. The value of this temperature is equal to EA upon 2R. At this temperature, the rate of change of slope is equal to 0. Before that, if you see, on increasing temperature, the slope is increasing, right? And after this point, we are getting that on increasing temperature, the rate of change of slope, right? The slope is going to decrease, right? So here, if you can say that before this, on increasing temperature, the slope is increasing. And after this point, on increasing temperature, slope is decreasing. So this temperature is very important for us. So sometimes while drawing the graph, we can draw the graph up to here, right? Exact graph is this, but it may possible that if I want to draw the graph up to EA upon RT, this will be the graph, right? It seems to be completely increasing, monotonously increasing, right? And then we can say after this temperature, the slope is going to decrease. So this is the complete graph. Now using this graph, what we can find out, right? So there is a question in JEE Advance. This is the question of JEE Advance 2010. Plot showing the variation of rate constant with temperature are given below. The plot that follows Arrhenius equation is, right? So many of us, when this question come in 2010, was saying that this is not, because most of the time we remember that okay, it has limitation. It is not that if we increase the temperature, it will continuously increasing. It is not possible. So most of us in our mind remember this part, right? That there is a limitation. If we increase, then further the rate of change of slope is going to decrease. But here they have not mentioned temperature. So this portion, initial portion, they have drawn till here, right? This temperature, we know that till here it is going to be, the rate of change of slope is going to increase. So this value is equal to E upon 2R. Right. So initially when this question came, many of us, we are saying that this graph is not complete, right? But it is complete. We have to understand that if the temperature is less than E upon 2R, this is Completely right. After that, it is rate of change of slope is going to decrease. So A will be the answer. Let us discuss effect of temperature on rate of reaction or rate constant of reaction. If two chemical reactions are taking place, in same temperature range, then larger the value of activation energy, more will be the temperature dependence of the reaction. So this we can see mathematically also. We have drawn a graph, right? Ln K versus 1 upon T, and there are two chemical reactions taking place in the same temperature range. Higher the value of activation energy, more will be the temperature dependence. We can write mathematically also, we can see that, because when we are writing this, the slope will depend on activation energy. Ln K is equal to ln A minus EA upon RT. So here, higher the value of activation energy, more will be the slope of this reaction. So this, if these two graphs are there, from that we can say that EA2 is greater than EA1. For same reaction taking place in different temperature range, the effect of temperature change will be more in low temperature range. Before discussing this, I want to discuss this mathematically. We can write that these two reactions are taking place, right? So for the first reaction, if I'm writing that, what is the value of ln K2 upon K1, and we are taking that the temperature range in which the reaction taking place is 300 Kelvin to 310 Kelvin. In this range, we are studying the reactions. Both reactions means initial temperature is 300 Kelvin. Then we have increased the temperature to 310 Kelvin. And we want to know that what is the effect of temperature on these two reactions. So ln K2 upon K1 for the first reaction is equal to activation energy of that reaction upon R. The difference of temperature is 10 Kelvin, and here we, in the denominator, we can write 300 Kelvin and 310 Kelvin. Similarly, for the second reaction, I can use the same formula, ln K2 upon K1. So activation energy of the second reaction, EA2 upon R. Difference of temperature is 10, and 300 and 310. So mathematically also we can see that this whole thing 10 R 300 310 is same, only EA is different. So higher the value of activation energy, more will be the effect of temperature on rate constant of the reaction or rate of reaction, because rate of reaction is directly proportional to rate constant. So this is about the first point. The second point is, for same reaction taking place in different temperature range, the effect of temperature change will be more in low temperature range. Yes, if we are carrying out the reaction and if we have increased the temperature at 300 Kelvin by 10 Kelvin, and then we are doing the same reaction at 500 Kelvin and increase the temperature to 510 Kelvin, then the effect will be more at 300 Kelvin. We can prove mathematically. So variation of ln K versus 1 upon T, it is a straight line. So for this same reaction, we are writing that at 300 to 310, the value is ln K2 upon K1 is equal to EA upon R. Difference of temperature is 10. In the denominator, this is 300 and 310. The same reaction is there, so activation energy will be same. Temperature difference is 10 Kelvin only, but the temperature is now 500 Kelvin, right? So you can see here that if I divide this 10 will cancel out, E upon R will cancel out, but here the denominator is less and here the denominator is more. So I can say that the effect of temperature change will be more at low temperature than that at high temperature. So these 2 points are very common in exam. Many objective questions based on this. So this is an example asked in JEE Advanced 2009. Paper 2. Let me read the question first. For the first order reaction, A will form P. So in most of the question, when we are asking the coefficient of the react, there is only one reactant and coefficient of the reactant is 1. The temperature T dependent rate constant K was found to follow the following equation. So this is the equation given by them. Log K. So be careful that ln and log, you have to be very careful, right? Most of us very casual when we are taking care of log K, right? So here log is there. So log means base is 10. The pre-exponential factor A and the activation energy A respectively is R. So it's a very simple question. Let me discuss this question. So they have given, let me write that what is the equation they are giving. So log k means base is 10 here is equal to minus times of 2000 1 upon t plus 6. So if I compare this equation by our Arrhenius equation, we are writing that k is equal to a e to the power minus ea upon rt. K is equal to a e to the power minus ea upon rt. If I am taking ln on both sides, ln k is equal to ln a minus ea upon rt. But here we don't have to use ln, we have to use log. So ln is converted into log by multiplying a factor of 2.303. So I can write this as 2.303 log k is equal to 2.303 log a minus ea upon rt. And then if we further simplify, we can write that log k is equal to log a minus ea divided by 2.303 r into 1 by temperature. So now if this is the first reaction and this is the second reaction, we can compare these two reactions. So on comparing, this is the intercept 6, right? So we can say that the value of log a is equal to 6. From there we can say that a is equal to 10 to the power 6. And on comparing, we can say that ea upon 2.303 r minus will cancel out. So I'm writing directly it is equal to 2000. So we have to calculate the answer in kilojoule, right? So we can write that 2.303 r kilojoule we have to write. So activation energy, if I find out that what is the value of activation energy, that is equal to 2000 into 2.303 into r. Since we have to calculate this value in kilojoule, r value will be 8.314. 8.314 divided by 1000, since it is in kilojoule. So this, if we simplify, we can write that this value is equal to 4.606 into 8.314. So by looking the options, we can find out that this value, right? So 16.6 cannot be possible. So it is greater than 32, right? So from there we can say that this D option is matching. D option is coming. The value of A is 10 to the power 6 and the value of activation energy is 38.8 kilojoule per mole. Now this is a graph, potential energy versus reaction progress, reaction coordinate graph. And this graph is according to transition state theory, right? So this graph, potential energy versus reaction coordinate, is related to transition state theory. So in this transition state theory, this is the reaction. Two molecules of Br and O in gaseous state, on colliding, they are converted into two molecules of NO and Br2. Here they have shown by this example, this is one molecule of BrNO and this is the other molecule of BrNO, and when they are approaching towards each other, this is the transition state, right? This is, here the potential energy is maximum. We know that when the molecules, gaseous molecules, will come together, right, when their distance is of the order of their diameter, then repulsive forces are dominating. So we are discussing that portion only here, right? Potential energy is increasing means we are saying that repulsive forces are dominating, and at this point what will happen, that the system has maximum potential energy, right? So after that, if the system will attain this condition, then after that it is converted into product. And from looking this graph, we can say that it is an exothermic, because the energy of product is less than the energy of reactant. So it is an exothermic process, and they have shown activation energy of this reaction. So this is about transition state theory. This graph is given in NCERT by taking this example, reaction between H2 and I2 to form 2 times of HI. And we have already discussed that the energy difference between average energy of reactant and product will give you delta H of the reaction, and H2 plus I2. This is also an example of exothermic reaction. So this is activated complex of maximum energy, which is known as transition state, right? We have drawn a graph like this. So in old NCERT, they have mentioned this type of graph where the circle is there. So in this region, there are many activated, the activated complex has many states, right? So this is the activated complex having maximum potential energy. Maximum potential energy means it's very unstable. After that, it is going to form the product. So that maximum energy activated complex is known as transition state. So things are given in NCERT, so be careful about that. When we are discussing, there are two type of theories: transition state theory and collision theory. So this is about transition state theory. From transition state theory, we can say that what is activation energy? Activation energy is the energy difference between threshold energy. From here to here, this energy is known as threshold energy. This is the threshold energy. So threshold energy minus energy, average energy of reactant molecules will give you activation energy. Collision theory, when we are discussing about collision theory, that according to collision theory, we are saying that fraction of molecules and kinetic energy graph, like in gaseous state, by using Maxwell equation, we have drawn a graph. Let me remind you that what was the graph regarding distribution of speed. So on x-axis, there is distribution of speed. On y-axis, there is fraction of molecules in a particular speed range. So dn upon n du. And if we draw this graph, it was near the origin, parabolic path is dominating, and away from the origin, exponential part was dominating. And if we combine them, this is the graph, right? So for this parabola, the axis will be the y-axis. Here, when we draw such type of graph, right, it is similar but not same graph, because here if you see the parabolic path, the axis of parabolic path is y-axis, right? If you convert from Maxwell equation, if you convert, since Maxwell equation is not in our syllabus, so that's why I'm not writing here. But from that equation, we can write distribution of kinetic energy of ideal gas molecules. So this is fraction of molecules in different kinetic energy. So on y-axis, it is similar to that. We can write that on y-axis, there is dn upon n d, and this epsilon is related to kinetic energy. So this is a range of kinetic energy. And here we are saying that, okay, this is kinetic energy on x-axis. So like this is known as most probable speed. Same way, this kinetic energy is known as most probable kinetic energy. So again, from there, we can calculate that what is the value of most probable kinetic energy. So they are not going to ask, because this Maxwell equation is not in our syllabus. So they are not going to ask about most probable kinetic energy. But there is a same way to calculate most probable kinetic energy, as we have discussed in gaseous state kinetic theory of ideal gas. So here, this is important. We are discussing fraction of molecules. Like if I calculate what is area under the graph, so area under the graph, because you can see here dn upon, and if I take different fractions here, right, this fraction will tell you fraction of molecules in this kinetic energy range. So if I add all the fraction of molecules in all kinetic energy range, what will happen? That in the numerator, it will become n, and denominator is n. So that is equal to 1. So we can say that area under the graph, right, is equal to 1. Area of this whole graph is equal to 1. So let us discuss here. They are discussing the effect of temperature on distribution of kinetic energy. So again, we can say that what is the difference in speed and kinetic energy? In speed, this parabolic path, the axis will be x-axis. It is not y-axis, right? For parabolic path, the axis is x-axis. So this is the x-axis for parabolic path, and then exponential part is dominating here, right? So similar, but there is a difference. This was y-axis, this is x-axis. So here we are discussing that in distribution of speed, we have discussed that at low temperature, the graph will be narrow. At high temperature, the graph will be wide. Same way here, we can discuss that at low temperature, the graph is narrow, right? And at high temperature, the graph is wide. So we can write here, this is important. We can say that the graph is narrow at low temperature and wide at high temperature. So this is one point which they can ask, because this is a graph given in NCERT. So this point is important. The second thing is when we are discussing activation energy, we have a doubt, right? So you should not have any doubt, because when we are discussing this transition state theory, then we are saying that, okay, when we are discussing about activation energy in this transition state theory, so this is the value of threshold energy, right? This is threshold energy, and this is the energy of a reactant molecule. So the difference of these two, we are saying that this value is equal to activation energy. So in case of transition state theory, we are discussing about potential energy, because reaction is taking place at constant temperature. So average kinetic energy of gas molecule, we can assume same, right? So this is about activation energy. This is according to transition state theory. But when we discuss collision theory, this value is activation energy. Here it is activation energy. So this activation energy is related to kinetic energy theory. We can say that it is the minimum kinetic energy which is required to give a fruitful collision, right? Molecules having energy greater than equal to activation energy can form product on collision. So this shaded graph is shown at low temperature. Low temperature is temperature T, and this अगर जिन molecules की energy activation या activation energy से ज्यादा है, वो collision करने पे product form करेंगे. So this is known as Boltzmann factor, e to the power minus E upon RT. This represents the fraction of molecules which on collision can form product. वो इस ग्राफ में इससे रिलेटेड, ये शेडेड एरिया जो है वो इस बोल्ट्जमैन फैक्टर को रिप्रेजेंट करता है, e to the power minus E upon RT. अगर मैं टेम्परेचर इंक्रीज कर दूंगा, तो टेम्परेचर इंक्रीज करने पे इस रीजन में द नंबर ऑफ पार्टिकल्स हैविंग एनर्जी ग्रेटर देन इक्वल टू एक्टिवेशन एनर्जी इज गोइंग टू इंक्रीज. तो ये जो पार्टिकल्स मैंने ये येलो कलर से शेड किया, ये एक्स्ट्रा पार्टिकल है. ये पहले वाले तो हैं ही, ये और एक्स्ट्रा इसमें ऐड हो गए, right? So they can ask question regarding that temperature coefficient when we are discussing temperature coefficient, right? Because other things will remain same. This is the dominating factor which will change. On changing temperature, the rate of reaction is increasing because of change in this factor. Exponential factor is increasing more because on increasing temperature, right? So this is this, now this whole shaded area is representing the fraction of molecules which can form product on collision, right? So this is very important. So these graphs can be drawn with the help of Boltzmann distribution of kinetic energy of gases. So these graphs are given, and the number of collisions with activation energy means those collisions which can form product is equal to total number of collisions e to the power minus E upon RT. So this is total number of bimolecular collision, and this factor is important. This represents fraction of collisions which can form product, right? So the rate of reaction depends on the multiplication of these two. So the number of molecules which has energy greater than equal to activation energy on collision can form product. So there is a, what I want to say, that activation Arrhenius equation is an empirical formula, right? So from experiment we have derived that K is equal to A e to the power minus E upon RT. Now that empirical formula can be explained by two theories. One is known as transition state theory, and the other theory is known as collision theory, right? So with the help of these theories, we are trying to derive Arrhenius equations, though we have not done those things, but the derivation can be done, right, on the basis of collision theory or in the basis of transition state theory. So when from theory, if we are deriving some equation, so that theoretical equations, when matching with experimental result, then it is fine. If it is not matching, then we have to modify that equation. So suppose if we are saying that modified form of Arrhenius equation, it is given in NCERT. This modified form of Arrhenius equation is given in NCERT, where they are saying that rate constant of a reaction is equal to, this is a steric factor, this is pre-exponential factor, and this is Boltzmann factor, right? So some modification is done in terms of steric factor. This steric factor is related to anything which is not matching with experimental and theoretical result. With the help of this factor, we can match it. Like if we are saying that the rate of reaction determined theoretically, with the help of formula, we have determined that what is the rate of reaction, And with the help of experiment, we have find out what is the rate of reaction. If both are matching, then there is no need of steric factor, or we can say steric factor is equal to 1. But suppose by formula we have calculated rate of reaction, right? So rate of theoretical reaction is less than experimental. So this theory is not valid because it is not matching with experimental results. So for this theory, what we have to do, we have to put steric factor which is greater than 1. So if I multiply this theoretical rate of reaction by this steric factor, then it will become equal to experimental value, right? So in this condition, we can say that steric factor is greater than 1. If rate of theoretical reaction is greater than that of experimental rate of reaction, then we have to make it equal. In order to make it equal, we have to multiply a factor which is less than 1. So steric factor will be less than 1. So these things are very simple, given in NCERT, and in past years in JEE Advanced they have asked question based on this. Temperature coefficient, right? So in temperature coefficient, we are saying that it is the ratio of rate constant of reaction at temperature T and temperature T plus 10, right? So higher temperature upon lower temperature, but difference of temperature should be 10 Kelvin. So if we assume that temperature coefficient is constant in a given temperature range, then we can use the formula to calculate the rate constant of reaction at T2 temperature if rate constant of reaction is T1 temperature is given, because K2 is equal to K1 mu to the power T2 minus T1 upon 10. But this is not always valid. This is valid when mu is constant, temperature coefficient is constant, right? So in question, if usually for chemical reactions, the value of mu lies between 2 to 3, not always that it is between 2 to 3. For some reaction, it may be less than 2. For some reaction, it may be greater than. We are talking about general value which lies between 2 to 3. It must be given in the question. So suppose I am taking an example where the value of mu is equal to 2, and the rate constant of the reaction at 300 Kelvin is K1, and the rate constant of the reaction we have to calculate at 340 Kelvin, right? That is equal to K2. So we are writing that we are increasing temperature in a step of 10 Kelvin, right? So moving from 300 to 310, 320, 330, and then 340. So we can write that from 310 to 300, 300 to 310. Temperature coefficient is K at 310 upon K at 300 multiplied by K at 320 to K at 310, and similarly we'll solve. So what this is mu, this is also mu, this is also mu, and this is also mu. So we have written that mu to the power 4. This value is mu to the power 4. If I simplify, so we are getting that K at 340 upon K at 300. So if we know K at 300, we can calculate K at 340. Many questions in mains, they have asked like this, right? But when you are solving, so मेंस क्वेश्चन को सॉल्व करने के लिए भी आपको ये पता होना चाहिए कि दिस फॉर्मूला इज नॉट ऑलवेज वैलिड. दिस इज वैलिड ओनली व्हेन म्यू इज कांस्टेंट. इफ दे आर आस्किंग इन जेईई एडवांस, वी हैव टू वेरी केयरफुल, बिकॉज अभी हमने थोड़ी देर पहले पढ़ा कि लो टेम्परेचर पे टेम्परेचर चेंज करेंगे तो रेट कांस्टेंट ज्यादा चेंज होगा. अगर हम हाई टेम्परेचर पे टेम्परेचर चेंज करेंगे तो रेट कांस्टेंट कम चेंज होगा. द इफेक्ट ऑफ change in temperature will be more at lower temperature than at higher temperature, right? So be careful about that, because when you are differentiating Arrhenius equation, you are getting that this temperature coefficient dk upon dt depends on temperature. It is inversely proportional to temperature square, right? So it depends on temperature. So in JEE Advanced, be careful about that. For mains question, we can see the data and we can assume that, okay, that can be solved when mu is assumed to be. Got it? We have also discussed that when the temperature is less than EA upon 2R, then the rate of change of slope will increase, and after that the rate of change of slope जो है वो decrease करता जाएगा. We have discussed that also. So let us solve one question. At room temperature 17 degrees Celsius, we are discussing the effect of temperature, and there is a lot of applications of effect of temperature on rate of reaction in food industry, in chemical reaction, in laboratory, right? So we are taking one example of that. At room temperature 17 degrees Celsius, milk turns sour in about 60 hours. If the refrigerator is at 3 degrees Celsius, milk can be stored 4 times as long before it sours at room temperature. How long should it take milk to sour at 57 degrees Celsius? Very common question. राइट, हमें पता है हमारी डेली लाइफ में ये यूज होता है। तो सबसे पहले ये मैं डिस्कस करना चाहता हूं यहाँ पे कि जो मिल्क के अंदर एक बैक्टीरिया होता है जिसका नाम है लैक्टोबैसिलस एसिडोफिलस, राइट। तो दैट बैक्टीरिया इज देयर इन फ्रेश मिल्क, और वो बैक्टीरिया अपनी पॉपुलेशन इंक्रीज करता है, और जब वो अपनी पॉपुलेशन को इंक्रीज करता है तो वो फर्स्ट ऑर्डर काइनेटिक्स को फॉलो करता है। तो यहाँ पे बाकी फर्स्ट ऑर्डर काइनेटिक्स से डिफरेंस ये है कि इनिशियली द नंबर ऑफ बैक्टीरिया इज लेस इन नंबर, राइट। सो वी कैन से दैट बैक्टीरिया इज एन नॉट. With time they are increasing their population. When they are increasing their population at any time t, the number of bacteria will be nt, and we are saying that the change in the population of bacteria dn upon dt follows first order kinetics, means it is k into number of bacteria at that time, right? So taking like terms on the same side, we can write that dn upon n is equal to k into dt, and if we integrate, then we are getting that ln nt upon n naught, राइट। केमिकल रिएक्शन में एन नॉट अपॉन एन टी होता है, यहाँ पे है एन टी अपॉन एन नॉट इज इक्वल टू के इंटू टाइम टी, बिकॉज हम जब केमिकल रिएक्शन लिखते हैं तो केमिकल स्पीसी टाइम के साथ डिक्रीज हो रहा है, लेकिन ये टाइम के साथ इंक्रीज हो रहा है, तो एन टी इज ग्रेटर देन एन नॉट। तो फर्स्ट ऑर्डर फॉलो करता है, बट दैट इज द डिफरेंस। तो नाउ कमिंग बैक टू द क्वेश्चन, हमें ये समझना चाहिए कि जैसे अगर हम रूम टेम्परेचर की बात कर रहे हैं, यहाँ रूम टेम्परेचर 290 केल्विन है, 17 डिग्री सेल्सियस है। तो यहाँ जब ये फ्रेश मिल्क है तो 17 डिग्री सेल्सियस पे इसमें कुछ बैक्टीरिया है, जैसे इसमें हमने 6 बैक्टीरिया शो किए हैं। अब जैसे जैसे टाइम बढ़ेगा ये नंबर ऑफ बैक्टीरिया बढ़ेंगे, और जैसे ही इन बैक्टीरिया की संख्या, द नंबर ऑफ द बैक्टीरिया विथ रिस्पेक्ट टू द इनिशियल वन हैज अ फिक्स वैल्यू, then the milk will change its taste, or the milk gets sour, right? तो ये वैल्यू फिक्स होगी, मतलब हम कह रहे हैं कि अगर पहले एन नॉट है और बाद में एन टी है, तो मिल्क को सोर होने के लिए, अगर सपोज ये पहले वैल्यू मैंने यहाँ पे शो कर रखी है 6 है, अब अगर ये वैल्यू इन डायग्राम्स में मैंने 12 शो कर रखी है, अगर ये वैल्यू 12 हो जाएगी तो हम ये कहेंगे कि ये जो है मिल्क खराब हो चुका है, ये अपना टेस्ट बदल चुका है, राइट। सो दिस रेशियो विल बी फिक्स, दिस ये आपको समझना पड़ेगा, चाहे वो 290 पे हो या वो 270 पे हो। हम स्टार्ट जब करेंगे तो फ्रेश मिल्क में नंबर ऑफ बैक्टीरिया 6 ही रहेंगे, और जैसे ही वे 12 हो जाएंगे तो हम कहेंगे कि ये मिल्क जो है वो खराब हो चुका है, ठीक है। तो अब हमें ये देखना है कि हाई टेम्परेचर चेंज करने पे ये कितनी जल्दी 6 से 12 होता है। वी हैव टू फाइंड दैट ऑन चेंजिंग द टेम्परेचर, व्हाट इज द टाइम रिक्वायर्ड टू बिकम 2 times, right? Here we have taken example 2 times, it can be any times, right? But we are taking here 2 times. Okay, so this is the concept. Let us now solve the question. 17 डिग्री को हमने केल्विन में, -3 को और 57 को केल्विन में कन्वर्ट कर दिया है। नाउ हमने अभी तक ये डिस्कस किया है कि राइट हैंड साइड व्हेन वी आर राइटिंग दैट k into t is ln n, या a नॉट नहीं होना चाहिए, यहाँ पे होना चाहिए at अपॉन a नॉट, at अपॉन a नॉट, या nt अपॉन n नॉट, राइट, ये होना चाहिए। तो ये वैल्यू तो फिक्स हो गई, चाहे हम 270 पे डिस्कस करें या 290 केल्विन पे डिस्कस करें, दिस इज फिक्स। So if I am discussing at 2 different temperatures, k into t is a fixed value. So I can say k1 t1 is equal to k2 t2. So in order to solve this problem, this is the concept that we have to use, k1 t1 is equal to k2 t2. तो अगर मैं ये लिख रहा हूं कि k at room temperature that is 290 Kelvin, 70 degree Celsius, उसमें टाइम जो लगा, we can see that the time taken is 60 hours. So I can multiply here that k into t and is equal to constant. अब अगर वो रेफ्रिजरेटर में रखा गया है तो we are saying that temperature is -3 डिग्री सेल्सियस, मीन्स कैलविन में टेम्परेचर हो गया 270 कैलविन, और टाइम जो लग रहा है वो 4 टाइम्स है रूम टेम्परेचर के। सो व्हाट वी आर गेटिंग हियर, वी आर गेटिंग दैट व्हाट इज द रेशियो ऑफ k at 290 अपॉन k at 270। सो वेरिएशन ऑफ रेट कांस्टेंट विद टेम्परेचर, राइट, यहां से हमें क्या मिल रहा है, ये वैल्यू है 4। Now we can use this formula, variation of rate constant with temperature ln k2 upon k1. So 290 k at 270 ln k2 upon k1 is equal to EA upon R, टेम्परेचर डिफरेंस यू कैन फाइंड आउट 290 और 270 में कितना टेम्परेचर डिफरेंस हो गया, 20 केल्विन का टेम्परेचर डिफरेंस हो गया। यहाँ हम लिख सकते हैं 290 into 270. So from here I can calculate that, and this value we know that this value is equal to 4. So from here I can write that the value of activation energy upon R लिख लेता हूं। ये वैल्यू किसके बराबर है, या मैं इसमें और कुछ कॉमन भी ले, ओके, एक्टिवेशन एनर्जी अपॉन आर की वैल्यू मैं यहां से लिख सकता हूं, दैट वैल्यू इज इक्वल टू 4 इंटू 290 इंटू 270 डिवाइडेड बाई 20। ये वैल्यू है। Now what I want to do, I want to calculate this value at 57 डिग्री सेल्सियस से, ये पूछा है ना, 57 डिग्री सेल्सियस मीन्स कैल्विन में हो गया 330 कैल्विन। सो नाउ आई एम राइटिंग दैट एट 330 कैल्विन, और यहाँ मैं टाइम निकालना चाहता हूँ, k इंटू टी, राइट हैंड साइड तो फिक्स है, ln nt अपॉन एन नॉट वो फिक्स है। नाउ आई कैन राइट दैट रूम टेम्परेचर पे ये वैल्यू थी 290 और टाइम लगा था 60 आवर्स। So from here I want to calculate ln K330 divided by K290, right? And that into time t is equal to, we can say this is equal to 60. So now I want to put this value, right? तो अभी मैं अगर इसको लिखता हूँ, what is this value? I'm taking ln on both side and then I am writing. So this is ln 4. This is not 4. This is ln 4. So here it will be ln 4. Okay. This is ln 4, ln 4. So now if I write here, what is the value of this? So we can use this formula, ln k at 330 divided by k at 290 is equal to EA upon R. The value of activation EA upon R is ln 4 into 290 into 270 divided by 20. This is EA upon R. T2 minus T1, temperature difference you can find out here. It is 40 upon T1, T2. T1, T2 is 290 and 330. So if I simplify this, 290 will cancel out. Further on simplification, this is 2 times. So we are getting 11 here and 9, 3 times 27. 9 into 2 is 18. Ln 4. We are getting this value. Or if we further simplify, we can say that the value of K330 divided by K at 290 is equal to ln, okay, so I am writing here ln, so ln 4 by 4 to the power 18 by 11. So taking anti-ln, right, so we are getting this value. अब अगर हम इस वैल्यू को यहाँ रखेंगे तो फ्रॉम देयर वी कैन राइट दैट द वैल्यू ऑफ टेम्परेचर टाइम, सॉरी, द वैल्यू ऑफ टाइम इज 60 इंटू, ये वाली वैल्यू यहाँ रख देते हैं, K330 अपॉन K290, सो दैट इज इक्वल टू 4 टू द पावर 18 बाई 11। और इसको हम फर्दर फिर से सिंप्लीफाई कर सकते हैं, वी कैन राइट दैट this 4 is 2 to the power 2, right? So this is 60 divided by 2 to the power 36 by 11. 36 by 11. If we have some data given, then we can solve. Okay, 16 to the power 9 by 11 they have given. Okay, so अगर मैं इसको simplify करूं तो मैं लिख सकता हूं इसको that this is equal to 60 and this is 16 to the power 9 by 11. We can simplify this. So this value we know that this is equal to 60 and 16 to the power 9 by 11 is given, that is 9.6. तो ये वैल्यू 9.6 है, मतलब 60 डिवाइडेड बाई 9.6। तो अगर आप इसको सिंप्लीफाई करेंगे, व्हेन यू सिंप्लीफाई दिस यू आर गेटिंग द आंसर गिवन हियर, विल गेट दैट 6.25 पावर, राइट? So we have discussed many concepts. First concept is for storing of milk. The population of bacteria raises from initial value to a fixed value at all temperatures. As we are increasing the temperature, the time required to achieve that will decrease. So at higher temperature, less time is required, which is 6.25. At higher temperature, at lower temperature, more time is required, which is 4 times the room temperature, right? So this is the concept. effect of catalyst on rate of reaction. When we are discussing the effect of catalyst on rate of reaction, this is related to, this graph is related to transition state theory. ये graph जो है वो transition state theory से related है, transition state theory. So in transition state theory we are saying that this is the activation energy for forward reaction. ये हो गई, ये threshold energy है, and this is the activation energy for forward reaction without catalyst. With catalyst, this is the path with catalyst. Without catalyst, if I calculate, this will be the threshold energy. ये threshold energy है और ये activation energy for forward reaction है. तो without catalyst, ये थोड़ा ग्राफ सही से नहीं बना है, right? So without catalyst, we are saying that activation energy will be more. If we are using the catalyst is decreasing the value of activation energy. यहाँ activation energy को catalyst कम कर रहा है, right? So this is according to our ट्रांजिशन स्टेट थ्योरी, राइट? सो ट्रांजिशन स्टेट थ्योरी में आप देखो रिएक्टेंट की एनर्जी में कोई चेंज नहीं है. देयर इज नो चेंज इन द एनर्जी ऑफ रिएक्टेंट मॉलिक्यूल. देयर इज नो चेंज इन एवरेज एनर्जी ऑफ प्रोडक्ट मॉलिक्यूल. एवरेज एनर्जी ऑफ प्रोडक्ट मॉलिक्यूल भी सेम है यहाँ पे. So catalyst cannot change the energy of reactant and product molecule. So it cannot change delta E or delta H of a chemical reaction. डेल्टा ई और डेल्टा एच को कैटलिस्ट चेंज नहीं कर सकता. दिस इज रिलेटेड टू कोलिजन थ्योरी. सो व्हेन वी डिसाइड कोलिजन थ्योरी, दिस इज द एक्टिवेशन एनर्जी, राइट? दिस ग्राफ इज रिलेटेड टू एक्टिवेशन एनर्जी. ये यहाँ पे ये जो पॉइंट है, दिस इज रिलेटेड टू मॉलिक्यूल्स हैविंग काइनेटिक एनर्जी ग्रेटर देन equal to activation energy, and these molecules can form effective, they will collide to form product. So uncatalyzed reaction में क्या हो रहा है कि एक्टिवेशन एनर्जी अभी ये है, अगर मैं कैटेलाइज कर दूंगा तो कैटलिस्ट एक्टिवेशन एनर्जी को कम कर देगा, लेफ्ट हैंड साइड में ले आएगा. तो ये एक्टिवेशन एनर्जी थोड़ी कम हो गई कैटेलाइज रिएक्शन की, तो इसमें फ्रैक्शन ऑफ मॉलिक्यूल्स इंक्रीज हो गए, एंड बिकॉज ऑफ दैट द रेट ऑफ रिएक्शन इज इंक्रीजिंग. सो इफेक्टिव कोलिजन्स मींस बोल्ट्जमैन फैक्टर जो है वो इंक्रीज कर जाएगा. बोल्ट्जमैन फैक्टर विल इंक्रीज इन प्रेजेंस ऑफ कैटलिस्ट, एंड बिकॉज ऑफ दैट रेट ऑफ रिएक्शन इज गोइंग टू increase. So there are many points regarding catalyst which can come. So one by one we are going to revise that. Catalyst will decrease the threshold energy, correct? Because this threshold energy is related to transition state theory. ये पहला ग्राफ threshold energy को catalyst कम कर रहा है. This is threshold energy in absence of catalyst, and this is threshold energy in presence of catalyst. यहाँ से लेके यहाँ तक ये पूरी एनर्जी जो है वो मैं डिस्कस कर रहा हूँ. ये थ्रेशोल्ड एनर्जी है यहाँ से, और अब हो गई ये वाली थ्रेशोल्ड एनर्जी. सो कैटलिस्ट जो है वो थ्रेशोल्ड एनर्जी को कम कर रहा है. दैट इज द फर्स्ट पॉइंट. द सेकंड पॉइंट इज कैटलिस्ट विल डिक्रीज द एक्टिवेशन एनर्जी ऑफ फॉरवर्ड एंड बैकवर्ड रिएक्शन बाय द सेम अमाउंट. यस, कैटलिस्ट विल डिक्रीज द एक्टिवेशन एनर्जी. ये दोनों थ्योरीज में वैलिड है, बट काइनेटिक थ्योरी ऑफ गैसेस में आप फॉरवर्ड बैकवर्ड नहीं दे सकते. ट्रांजिशन स्टेट थ्योरी में यू कैन सी दैट इन केस ऑफ ट्रांजिशन स्टेट थ्योरी, दिस इज द एक्टिवेशन एनर्जी ऑफ फॉरवर्ड रिएक्शन इन प्रेजेंस ऑफ कैटलिस्ट, एंड इट इज एब्सेंस ऑफ कैटलिस्ट. दिस इज the activation energy of backward reaction in absence of catalyst, and this is the activation energy of backward reaction in presence of catalyst. So catalyst is decreasing the activation energy of backward and forward reaction by the same amount. Same amount से ये decrease कर रहा है, and that is this amount, right? Next point is catalyst will increase the value of K forward and K backward by the same factor. That is fine, because अगर हम Arrhenius equation use कर रहे हैं तो A तो fix है. What is happening? EA minus X, right? तो activation energy change हो रही है. Due to change in activation energy, what we are finding that rate constant is going to increase. Due to increase in rate constant, rate of reaction is going to increase. So using catalyst will increase the number of fruitful collisions, right? Boltzmann factor will increase. Fourth point, catalyst cannot change delta H. That is obvious. यहाँ से देख सकते हैं हम कि catalyst delta H को change नहीं कर सकता, delta E को change नहीं कर सकता. Catalyst cannot change equilibrium constant. That is also correct, because when we are writing that delta G is equal to delta H minus T delta S. So delta G naught is delta H naught minus T delta S naught. We can see like this, or we can see equilibrium constant जो होता है वो K forward upon K backward होता है. So what is happening that when we are writing equilibrium constant in absence of catalyst, it is K forward upon K backward. If we are writing equilibrium constant in presence of catalyst, this is equilibrium K forward in presence of catalyst upon K backward in presence of catalyst. K forward in presence of catalyst is K forward without catalyst e to the power x upon RT. Same way I can write that K backward e to the power x upon RT, because EA forward minus x and EA backward minus x. So if I simplify, this factor is common. So there is no effect on equilibrium constant by the catalyst. Catalyst cannot change the value of equilibrium constant. If catalyst cannot change the value of equilibrium constant, catalyst cannot change delta G naught reaction. Delta G naught is minus RT ln equilibrium constant, means it cannot make a non-spontaneous reaction spontaneous. Catalyst cannot change average energy of reactant and product molecule that we have seen in this graph. ये जो है average energy of reactant molecule है, and this is average energy of product molecule, and catalyst is not able to change the average energy of reactant and product molecule, right? And the last point is catalyst can increase the number of fruitful collisions that we have already discussed. So these are the important points regarding catalyst. And this is one simple example. Let me read this example first. In gaseous reactions, important for understanding the upper atmosphere, H2O and nascent oxygen react bimolecularity to form two OH radicals. Delta H for this reaction is 72 at 500 Kelvin. So let me write in mathematical form what they are saying. ये कह रहे हैं कि H2O molecule gaseous state में है और nascent oxygen gaseous state में upper atmosphere में, और ये reaction हो रही है, and they are forming two free radicals of OH. Delta H for this reaction they have given, that is equal to 72. Endothermic reaction है 72 kilojoule per mole. This is happening at 500 Kelvin. Activation energy for this forward reaction, I can say that EA forward is equal to 77 kilojoule per mole. Then calculate activation energy of bimolecular recombination of two times of OH radical to form H2O, and means they are asking about what is EA backward. So EA backward and EA forward, we have discussed that delta H reaction can be written as EA forward minus EA backward. So from here we can calculate that EA backward is equal to EA forward minus delta H. EA forward they have given, that is equal to 77 minus EA backward, that is 72. From there we can find out that this value is equal to 5 kilojoule per mole. Very simple question, but it's important for JEE Main. So this is the activation energy of backward reaction. And one more example is there. Let us go through this example. They are saying that the Arrhenius equation for two first order reaction is given. A will form B and C will form D is given by K1 is equal to 10 to the power 12. So this is the value of A, and the value of A is very high, 10 to the power 12. E to the power minus EA upon RT. So this is activation energy of this first reaction. A will form B, and the second reaction is K2 is equal to 10 to the power 11 E to the power minus EA upon RT. So this is activation energy of forward and backward reaction. This is given here. So at what temperature K1 becomes equals to K2? So it's mathematical equation. K1 and K2 are equal. We have to write K1 is equal to K2. So from there we can write K1 is 10 to the power 12. Activation energy E to the power minus activation energy, that is 81.28 upon RT. On the right hand side I can write that this is 10 to the power 11 E to the power minus 43.10 upon RT. So if I simplify this from here, this is 10, right? If I take this, this is 10. और इसको मैं उधर लेके जाता हूं तो I can write that this is equal to 81.21 0.28 minus 43.10 upon RT. And if I simplify this, if I take ln on both sides, I can write that ln 10 is equal to ln of this value is 81 minus 43. We can do the calculation. 81.28 minus 43.10 divided by the value of R should be 8.314. 8.3 they have mentioned in the question, and they have given the value of ln 10 is equal to 2.3. So 2.3 is equal to, here temperature is there. So if I simplify this, 81.28 minus 43.10. So this value will be 11 minus 3 will be 8, 7 minus 38.18. So I can write that this is 38.18 upon 8.3 into T. So from there I can get the temperature. Temperature is equal to this value they have given in kilojoule, right? So this value should remember that this is in kilojoule, and when we are writing R, I am writing in joule. So I have to use this factor, right? So temperature is equal to 38.18 divided by 8.3 into 2.3, and this will be 1000. So if you simplify this, right, multiply 8.3 by this value, right? So you can write that 8.3 into 2.3, you will get 9 and 24. This value will be 6 and 16. So 9, 10, 11, and this is to 21.09. So if you simplify, this is 38.18. And this value, if you find out that we are getting 8 and 9, sorry, this is 9 and this is 18. So this we are getting 19.09. 19.09 into 1000. So we are getting exactly 2000, right? So the temperature is 2000 Kelvin. At 2000 Kelvin, we are getting this answer. Okay, right. So what we have discussed, that rate of a chemical reaction depends on rate constant, and rate constant depends on temperature and activation energy. And we can change the rate of a reaction by changing the temperature and using catalyst. Similarly, when we are solving questions, we are writing for first order KT is equal to ln A0 upon AT. The value of rate constant does not depend on concentration or time, but the rate constant depends on temperature. On increasing temperature, rate constant is always going to increase, right? So K is increased, right? So KT is equal to ln A0 upon AT. Half-life, we are writing that half-life is equal to ln 2 divided by rate constant. So on increasing temperature, rate constant will increase, means half-life will decrease. यदि आप लोगों को हमारा वीडियो पसंद आ रहा है तो प्लीज इसको लाइक जरूर करें. थैंक यू.